and then let's move on. Now we have Professor Gergely Endrodi, and he will talk to us about the magnetic susceptibility of QCD matter. Gergely?
Right, thank you. Let me share my screen.
Efrain, could you please stop sharing your screen?
Yeah,
Thank you.
Sorry.
Thank you.
Done. Yeah, okay.
Do you see this now?
Not yet. Now we see. Excellent. Go ahead.
Okay. So thanks a lot for the introduction and also for the invitation to this workshop. Today I'm going to talk about the magnetic susceptibility of QCD matter. This is work done in collaboration with Gunnar and Stefano from Regensburg. So that means I'm moving a little bit away from the topic, which so far was more like the phase structure, the phase diagram of QCD with a magnetic field. And instead, I'm going to focus on the equation of state, which, as we all know, is also a very important characteristic of strongly interacting matter. It gives the equilibrium description of QCD matter, the relationship between the energy density and the pressure. And this is an important ingredient for a series of different systems. You needed to solve the Friedmann equations, which tell you how the early universe evolves. It is entering the TOV equations, which are necessary to solve for the mass-reduced relation of neutron stars. And it also is a relevant input for the evolution of heavy ion collisions that drive from the quark-gluon plasma phase through hadronization towards freeze-out. And in each of these three situations, magnetic fields, strong magnetic fields can be present, modifying the EOS and having some potentially relevant implications. I'm not going to introduce now the details, or I'm not going to speak about the relevance of magnetic fields to this audience. Most of you know this very well, and this was already covered to a certain extent by the previous speakers already. This is how the equation of state looks like at zero magnetic field. It is encoded in one relationship, for example, in the pressure, in the relationship or in the functional dependence of the pressure on the temperature. And this can be calculated on the lattice. There is no sign problem involved. One can calculate the full equation of state. And this is a plot that most of you will know about the pressure, the entropy density, and the energy density, or the trace anomaly as a function of the temperature for two different groups, and nice results. And now when you go away from the zero magnetic field limit, you have an additional functional dependence on the magnetic field. Now I'm going to, in this talk, I'm going to assume that the magnetic field is small. So there is one term in the equation of state which describes the quadratic dependence on the magnetic field. And this will be encoded in this permeability or susceptibility function that I'm going to introduce in a moment. So this is an appetizer of what is going to come today or in this talk. I'm going to explain to you how this can be calculated on the lattice and what kind of implications it has that this permeability function looks like this. And you can find the details in this paper. By the way, all the links that you can see in my talk are clickable. So if you look at the PDF, you can just click them and you get to the Inspire web page. So this is the outline. I'm going to introduce the permeability, define it in some more detail, and then look at how one can calculate this on the lattice. There is one particular problem or issue, the flux quantization issue, that we are going to discuss in more detail. And I'm going to tell you about a new technique to overcome this issue. And then I'm going to just present the results. And at the end, I will spend some time on separating the results for the susceptibility into two different contributions, from spin and from angular momentum related contributions. All right, so we have the free energy density, F, that is going to be the starting point for our discussion, and it depends on the magnetic field. I can differentiate twice with respect to B, then I get the first non-trivial contribution, and this is the definition of my magnetic susceptibility. And from this, all the quadratic contributions to the equation of state can be reconstructed for the pressure, for the entropy density, and for all different quantities that you might be interested in. Now, this is not the full story. Besides this term, with the magnetic susceptibility, there is another term which just comes from the fact that the magnetic field itself carries energy, just the classical energy B²/2. We are dealing with a constant homogeneous magnetic field. And these two terms can be just combined into B²/2 mu, where mu is the permeability. I'm following here the notation of Landau-Lifshitz. That we can have two different types of materials. Either the permeability is bigger than 1, that means the susceptibility is positive, then we have paramagnetism, or mu can be smaller than 1, in which case the susceptibility is negative, then we have diamagnetic materials. And all materials in nature can be classified into these two cases. By the way, E here is just the elementary electric charge, just a constant that I'm defining here, that I'm merging here into the definition of chi for simplicity and convenience. All right, so you have paramagnets and diamagnets, and they behave very differently when they are exposed to magnetic fields. Paramagnets are attracted to magnetic fields, and diamagnets repel the magnetic field, which you can visualize like this here. This is a snapshot from an experiment where liquid oxygen is poured onto an experimental setup where a very strong magnetic field is created here in the middle. And the paramagnetic nature of liquid oxygen causes it to overcome the gravitational force and stay there in the region of space where the magnetic field is the strongest, showing that it is indeed a paramagnet. On the other hand, the frog, mostly containing water, is diamagnetic, so it will levitate on top of a magnet. Now, QCD matter or QCD medium at non-zero temperature can also be thought as a medium, and therefore it also has a magnetic susceptibility describing its response. And now we can guess how it looks like as a function of the temperature, this susceptibility function, from very simplistic or very simple arguments without actually carrying out lattice simulations. So in the vacuum, we have unity for the permeability, so the susceptibility has to start from 0. On the other hand, when you go to very high temperatures and we have quark-gluon plasma, according to the asymptotic freedom property of QCD, there are free quarks or quasi-free quarks roaming around there. Most of the effect for the interaction with the magnetic field comes from the spins. And the spins of these quarks align with the magnetic field, so they decrease the energy, which means that we have a paramagnetic response. We have a large positive result for the susceptibility here. There is yet one more region of QCD where we can approximate it with some simpler model, namely low temperatures, where QCD is to the lowest approximation just a bunch of pions. Is there a question?
I can't see any, no.
All right, so I just heard someone. So low temperatures, we can approximate QCD as a bunch of charged pions. Now they don't have spin, they just respond to the magnetic field via their orbital angular momentum. And then we know from Lenz's law of classical electrodynamics that this is always counteracting the magnetic field, leading to a diamagnetic response and a negative susceptibility. So roughly this is the picture that emerges. The susceptibility should start from 0, it then should go negative, then it should turn positive. So there should be some point at which it again crosses 0. And this should basically be somewhere where the pionic regime is separated from the quark regime, so around DC. Now let's do lattice simulations to check this picture and especially calculate it in more detail. We are facing one particular problem on the lattice, and this is the flux quantization problem. Our results or our simulations are done in a finite volume with periodic boundary conditions. That means that we are on a torus, and now I'm borrowing this picture from Massimo's paper from a couple of years ago, which explains the story in a very nice way. Assume that you have a quark which you translate or you you propagate along a closed surface, or along a closed contour, sorry, on the surface of your torus, then it picks up a phase factor, which is nothing else but the exponential of the contour integral of the vector potential which corresponds to the magnetic field. Now you can employ Stokes' theorem to rewrite the contour integral as a surface integral of the magnetic field through this area A, which is enclosed by the contour. So you just get B times the area A in the exponent. But since you're on the torus, the contour can also be thought of as the contour of not the area A, but everything else minus the area A. And then you get a minus sign because the contour is counterclockwise. And in this case, you end up with this expression. Nevertheless, the phase factor should be unambiguous and single-valued. So this is only consistent, that these two lines are equal, if the magnetic field satisfies this consistency equation, which means that the magnetic flux, the magnetic field times the area of the torus, is 2 pi times an integer. Q is the charge of your quark, which can be for the up, down, and strange quarks 2/3 or -1/3. So the smallest charge is the down quark. And in that case, your EB, elementary charge times B, has to be 6 pi times an integer over the area of your lattice. That means that the magnetic field is a discrete variable in your finite volume. Therefore, differentiation with respect to B is ill-defined. You just cannot evaluate the derivative with respect to B in a way that you are used to when you are, for example, dealing with chemical potentials. There have been several workarounds developed in the last 5-6 years. And here I'm just recapping them very, very briefly. The first set of methods is maybe could be referred to as an integral type method, even though it's called finite difference method by the PISA group. The idea here is that you calculate the total free energy numerically for a set of different values of this flux quantum, and then you differentiate numerically. This is pretty expensive computationally. The other idea put forward by Levkova-Detar in 2013 is to not work with constant magnetic fields, but by so-called half-half magnetic fields, where half of your lattice has a positive and another half negative magnetic fields. Therefore, you have zero flux, and the amplitude of the magnetic field can be varied continuously, and then you can differentiate. This works, but unfortunately, it introduces large finite size effects because of the jump in the magnetic field. One can also relate the magnetic susceptibility to differences between pressures. Some of you will know that in the presence of the magnetic field, you can define a longitudinal and transversal pressure, and the two are not the same, and you can calculate the difference of the two, and this is related to the magnetization. On the lattice, for this, we need anisotropic lattice spacings, and this is also a technical challenge, which causes a lot of problem, actually. Therefore, I'm suggesting a new method here to express the magnetic susceptibility as an operator in the thermodynamic limit, and then use it in finite volumes. This is our latest paper where we explain this. All right, so how does this work? I'm just going to sketch the method here. Not going to go into the very details. The idea is to take basically a detour. Instead of looking at a constant homogeneous magnetic field, which we know have a quantized flux, we approach this constant magnetic field via oscillatory fields. So imagine that you have a magnetic field which has some momentum P1 in the x1 direction and oscillates like that. And then you make this P1 momentum smaller and smaller, so the wavelength larger and larger. And at some point, you will recover a homogeneous background in the limit of P1 going to 0. How does this work? Now, if I have the path integral depending on the magnetic field in this way, the magnetic field enters via the vector potential and couples to the electric current, electromagnetic current, which takes this form. Now I have these oscillatory magnetic fields, which are represented by oscillatory vector potentials. Then I can just differentiate twice with respect to the magnetic field amplitude, and I get something like this. Without going into the details, I have a current correlator, and I have some convolution with the kernel depending on coordinates. The nice thing is now that the expectation value, so the average over gluon and quark fields, is only here in the current correlator, which knows nothing about the details of the magnetic field. Everything about the magnetic field is outside the expectation value in this kernel. So the only thing to calculate on the lattice is this expectation value of the current correlators. And this has very many nice properties, like, for example, it is translationally invariant, and one can use this together with a couple of trigonometric identities to arrive at a simpler formula, which looks like this. So for this oscillatory susceptibility, we have this current correlator, which I rewrote now into this projected form, but it's still the same current correlator. And now there is only one more integral left to do, which has this form containing the x1 direction. This is the direction in which the magnetic field oscillates. And now the nice thing is that we can take the zero momentum limit if we are in an infinite volume. Then this kernel here just becomes a quadratic kernel, and we get this simple expression. How does this look like typically? Well, there's an exponential fall off in the current correlator. So these current correlators fall off with the vector meson mass, or 2 times the pion mass, whichever is the smaller. Anyway, they fall off exponentially, and then there is this quadratic kernel which modifies this fall off slightly. Now you might have spotted that I was cheating a little bit when I made when I took the 0 P1 limit, because this is only possible in an infinite volume. Whenever I'm in a finite volume, then this P1 variable is also discrete. This means that this formula is not quite right. True, when I'm in a finite volume, now I have to watch out about my periodicity in my volume. For example, the current correlator is not just an exponential, but it's a cosh. So it has 2 exponentials, one coming from left and one coming from the right. Very similarly, the kernel can also be symmetrized to comply with these periodic boundary conditions to be this kind of symmetrized quadratic kernel. There is a problem with this kernel, namely it has some non-continuous or non-smooth dependence at the middle of the volume, but that is not a problem, this kind of cusp, because this is anyway multiplied by an exponentially small current correlator, so this is not problematic. To show to you that this is indeed doesn't introduce large finite volume effects, I'm plotting here the lattice results for the correlator for 2 different volumes. And you can see that on the smaller volume, we turn back at the middle of the lattice, and on the larger volume, we can go farther away until we hit the middle of the lattice and then turn back. The contribution to the susceptibility, nevertheless, is basically the same for both of these volumes, and we have a very nice smooth dependence on this momentum quantum, and we can indeed take the 0 momentum limit even on finite lattices without introducing large finite size effects. So this is a very large advantage over the half-half method I talked about earlier. By the way, if you also look at these finite momentum results for the susceptibility, they turn out to be relevant or actually analogous to the vacuum polarization function form factor, which appears in the mu and g minus 2 calculations. Those are typically done at 0 temperature. Basically, what we did here is to generalize that to finite temperatures. Okay, let's see how the results look like. First of all, at 0 temperature, we can do these calculations. And here I'm plotting this magnetic susceptibility as a function of the logarithm of the lattice spacing. And I'm choosing this funny variable here because you can see it is basically linear. The result is completely linear in this variable, which reflects nothing else but an additive divergence in the bare magnetic susceptibility, which is well known already since Schwinger. And it is there because of electric charge renormalization. This has to be subtracted by taking a difference between the bare susceptibility at finite temperature and 0 temperature. Here I'm also plotting.
Literally 5 minutes.
Yep, speeding up. I'm also comparing here to earlier methods which lie on top of our results. Now, going to finite temperatures, taking the difference between finite T and 0T gives us this set of results and a continuum extrapolation, which, as you can see here in the inset, goes negative owing to the smallest lattice spacings that make the continuum extrapolation more reliable. So I'm just showing here the continuum extrapolation and making contact to a hadron resonance gas calculation at low temperatures and a perturbative calculation at high temperatures. A completely smooth dependence is visible, and basically we understand the whole regime. A comparison to the other methods available in the market show slight discrepancies here in the transition region. These we think are due to continuum extrapolation issues and should be clarified in the near future. So this is the final result again, now expressed for the permeability, and there is also a parameterization that we provide. If you click on this link, you get a Python script which produces to you, using this parameterization, all the different observables in the equation of state that you might want to use in your model or wherever you think it is necessary to use. All right, so in the last couple of minutes, I would like to speak a little bit about an additional theoretically interesting notion for the susceptibility, namely its decomposition into spin and angular momentum. Well, for free fermions, we know that there are two basic effects that tell us how the magnetic field interacts with the fermion, either via its spin or via its orbital angular momentum. And for a free fermion, where for an electron that only interacts with the magnetic field, the two effects have this kind of relationship to each other. The Pauli paramagnetism gives a positive contribution to the susceptibility via the spin effect, and the Landau diamagnetism gives a negative contribution via the angular momentum. So this is for free particles, and it is well, pretty interesting how these concepts survive when you consider a strongly interacting quantum field theory description. Well, things of course become much more complicated, but at least in this interacting case, what still holds is that the Dirac operator through which the magnetic field couples to the quarks separates into a spin term, magnetic field times this spin operator, plus a rest at least, which contains all these angular motion. And now if you look at this spin term, what you have to do basically is to carry out a path integral over quark and gluon fields, and you end up with an expectation value involving the spin operator, which is this fermion bilinear containing this tensor structure. And then you can show that the spin contribution to the susceptibility takes this form. It is the magnetic field derivative of this fermion bilinear times some function, which I don't have time to explain now in detail, but I have a backup slide about it if there are questions, or we can get back to this in the discussion session. So here is how this fermion bilinear looks like as a function of the magnetic field. It starts off linearly, and what you need here is really this slope, which I will refer to as tau, which depends on the temperature and has some non-trivial dependence on T. Incidentally, this tau f has also some experimental relevance. It is related to the normalization of the leading twist photon distribution amplitude, and therefore it is very important for deep inelastic scattering. One can calculate this tau f very similarly to the magnetic susceptibility, the full susceptibility. It also undergoes additive renormalization by a subtraction at 0T. And on top of that, it also undergoes multiplicative renormalization by the tensor renormalization constant because of this tensor structure basically here. This ZT was calculated also non-perturbatively on the lattice. And this is the result for the light quark, for example. Again, we do a continuum extrapolation. And putting that into our formula, we get the spin contribution to the susceptibility, which starts off from 0, then goes negative, and then turns back and apparently wants to get positive at some point, but our temperatures are so far limited to this regime. The light yellow band here is a systematic uncertainty related to the fact that we have to do this zero quark mass subtraction in this formula. And it is pretty challenging. All right, now I'm coming to the end. I can define the angular momentum term indirectly by taking the full susceptibility that I had and subtracting the spin term. This is the full susceptibility, the blue one. This is the spin term, the yellow one. And the result of the subtraction is this gray curve, which looks like this. And this leads us to a very intriguing picture. For very high temperatures, where we have this free case relationship between the Pauli paramagnetic and the Landau diamagnetic terms, we have that the two contributions compare to each other like 3 and -1. But in the QCD regime, we have a completely different picture. The spin term is negative, the angular momentum term is positive, and they give rise to a large cancellation in order to produce the full thing. Notice that if you go to very high temperatures, you see that the spin term goes positive, the angular momentum term goes negative, and you will recover this free field picture. And while I don't have a full answer to why this is so different compared to the high temperature regime, the answer must lie in confinement and in the interplay of confinement and spin physics. Namely that when you have confinement and, for example, charged pions as effective degrees of freedom, here you have quarks and anti-quarks that have spins opposite to each other because they are confined in a meson. And therefore, only one of the spins can point in the direction of the magnetic field, and the other is forced to be off the angle or anti-parallel to the magnetic field. And this causes a large positive contribution to the energy. Bless you. So this brings actually me to the summary. I showed a new method to calculate the magnetic susceptibility directly at zero magnetic field in finite volumes without having to worry about finite volume effects. And using this method, we can really pin down the dependence of the susceptibility on the temperature for a broad temperature range, seeing that pions being diamagnetic give a negative contribution, so a permeability below 1, quarks giving a positive contribution, so permeability much above 1. And there is a non-trivial decomposition of this into spin and angular momentum terms, which are quite surprising as they deliver basically the opposite of what you might expect from a free field picture. Thank you very much for your attention.
Thank you, Gergely. Time for questions. I don't see any raised hands.
There is one.
Oh, sorry. Aha, Oleg, please.
Yes, yes, yes. Thanks, and thank Gergely for interesting talk. I have a question concerning the magnetic flux quantization, and actually the just proof which you presented is quite similar to the Witten proof of quantization of magnetic monopole, right? And so this means that here, if you have a non-zero flux through compact surface, it's analogous to magnetic monopole. So the whole effect emerges because of the non-zero flux through compact surface, that is from the periodic boundary conditions. And maybe it's possible to avoid this problem by taking some other boundary conditions, non-periodic ones.
Yeah, that's true. That's true. But then we are actually used to, well, we don't like non-periodic boundary conditions on the lattice because that usually give us large finite volume effects. And this is just a way to reconcile these periodic boundary conditions with a constancy of the magnetic field. But I agree with you that if you drop the periodicity in your boundary conditions, then you can also get away with this.
So this means that somehow you generate something like Dirac monopole on the lattice, right? in a sense, by periodic conditions.
In some sense, yes. Actually, Massimo has a very nice picture about this for their finite difference method, where they show that that if you make this flux quantum tiny bit non-integer, then you can show that what appears is basically a constant magnetic field plus a Dirac string at one point of your lattice that becomes invisible only when you have integer quanta, and for other values you have this additional contribution that you don't want actually. Maybe Massimo can comment on that later.
Yes, that's true. I mean, yeah, you can see the sort of Dirac string in this way. Maybe we can look at the picture in the discussion session if you want.
All right, sounds good. Akio?
Yes, this is Akio, and I have a maybe related question to the flux quantization. So if I understand correctly, that boundary condition at the finite volume related to the gauge invariance for the U1, right? And how to say what is in your new method?
Can you repeat the question, please?
Sorry, the flux quantization is related to the gauge invariance for U1 field, right?
Okay, I mean, as we just discussed, it is basically coming from the periodic boundary conditions for the vector potential. I mean, if you wish, the existence of the vector potential is coming from gauge symmetry, or
I mean that usually we use in the Landau gauge for the U1 field, right? So that gives the boundary condition for the fermions.
I mean, if you look at this page, I'm starting off with a vector potential, and I haven't specified what gauge I'm using. I might use Landau gauge, I might use the symmetric gauge, I might use whatever I want. In the end, the quantization only cares about the flux of the magnetic field, and this is like again typical of such Aharonov-Bohm type experiments or problems where you have a dependence on the vector potential, but in the end only the flux of the magnetic field is what matters. So does this answer your question? I'm not sure I understood what you mean.
Maybe we can discuss later. Thank you.
Okay, thank you. I don't see any more raised hands, but if anybody wants to pose a question, please speak up. If not, let's thank again Gergely and move